My name is Colson Cunningham. Welcome back to another installment of Physics 2212. This is Lab 2, Charge Tapes Reusable. The purpose of this experiment is to create a computation model to improve upon the previous charge experiment while showcasing knowledge on its principles. Principles at stake here are the Coulombic force, also known as the electric force, and the gravitational force, as well as the charge on everyday objects. The electric force is equal to kqq over r squared, where k is a fundamental constant, r is the distance between two point charges, and q is the charge on each point charge. Gravitational force is equal to gmn over r squared, or as we'll use it in this model, mg, where m is the mass of the object and g is the average acceleration due to gravity on our surface. Expectations are that there will be more electrons on the tape computed in model 2 than in lab 1, that this model will be a lot more accurate than the first lab was, and that the tape will be balanced, meaning that it is in equilibrium. Assumptions made include ignoring the interactions between the tiny pieces of charge dq within each separate tape, that the electrons are evenly dispersed and exist solely on the underside of the tape, and that both U-tapes have equal magnitudes of charge. Here's some of the math involved in this lab. We have the computation for the first gravity, and that's the same as the first lab. We're going to say, because it's in equilibrium, we're going to say that the electric force is equal to the gravitational force, and we have a double integral set up here, which is really just a fancy way of saying that we're going to sum up the tiny pieces of electric force calculated between each dq on the top and the bottom tapes, and using our lab 1 approximation and that charge calculated, we see that the Coulomb force is not equal to the gravitational force, which means that that is wrong. Using second lab's model, I was able to calculate the Coulombic force that is equal to the gravitational force, and from that, the amount of charge on the surface of the tape, and therefore the number of electrons needed on the surface of the tape to equal the gravitational forces. And that number yielded an error value of over 2,700% from lab 1. Here's the code used in my experiment. We have the top tape, which is the system. We have the bottom tape. We have the gravitational force due to the surroundings on the system. And we have the electric force, which is due to the bottom tape on the top tape. As well as each of these arrows is a tiny piece of the electric field calculated on each dq. And you can see the dq's, where the tiny piece of electric field on the edges has a lot bigger x component to the electric force than the ones in the middle. Here are the constants and data copied over lab 1, and that includes the distance between tapes of 2 centimeters, a tape length of 30 centimeters, and a tape mass of 3 times 10 to the negative 4th kilograms. Here is my function for the electric field, as well as the charge functions, which is just the 100 different point charges used to approximate each tape. Here is the top tape and the bottom tape, as well as the electric fields and forces calculated across all 100 points on the top and bottom tape, and the arrows associated with them. Between the two labs, lab 1 had different lengths, that's different charges on each tape, but the charges were assumed to be congruent at 1 point, as well as the tape is assumed to be only 1 point, and the charge is supposedly equal on both pieces of tape. In lab 2, there's nothing to interfere with charge on the tape, like my hands. The tapes are the same length, and the charges evenly distributed between 100 different points along the length of the tape. And the tape is approximated to be a line rather than the rectangle it is. Charge is still equal on both sides of the tape, if that's what we're doing. So if we had treated this like a point charge, like in the previous lab, the calculations would be a lot easier. But there needs to be more electrons in the line charge model, as there's an x component in the point, as there is no x component in the point charge model, whereas in the line charge model there is an x component, as I pointed out at the end. In the x component, as the x component increases, the y component decreases for each individual piece of the electric field, yielding in a smaller net electric field in the y direction, meaning more electrons are moving. Why these differ? Like I said, the line charge model is going to be much closer to the real value, as it is more practical in the real world setting. Point charge congregates all charge into one location, which completely disregards the possible for x components. And the x component is going to decrease net electric field in the y component. And so the smaller distances between point charges means that there's a smaller radius, meaning a stronger field.